Good morning, everyone. This is Alex Bassini again with AWC webinar number 40. Thank you for tuning in. We did take a bit of a break there for a couple months. Now these are going to be pre-recorded. We're no longer doing them live. I think it's just a little easier for us to schedule everything around our busy schedules. So today I'm joined by Jay Garcia from NX Filtration. Today we're going to be covering hollow fiber nanofiltration. I love this concept. I love getting an existing membrane or process or tool and looking at ways that we can enhance it and do better. So thank you, Jay, for being here. So with that, just a quick little background on AWC and what we've been doing. This is part of the AWC webinar series. We've been doing them. Now we're at number 40. Wow. So today, of course, we're covering hollow fiber. A little on AWC. We've been around for 40 years. We design and build packaged water treatment plants, close to 600 plants worldwide. We divide everything into three categories. So we've got everything that has to do with potable water treatment. We've got wastewater treatment, packaged wastewater treatment, and of course, skid-mounted systems. When we look at hollow fiber nanofiltration, this would be part of more of a skid-mounted systems and would likely be paired up with other processes or technologies, much like dissolved air flotation, clarifiers, tube settlers, etc. But with that, enough about us. We're going to get started with hollow fiber nanofiltration. So Jay, take it away.
Thank you, Alex. Yeah, I really appreciate this time to speak about our technology. And I'm going to be talking about hollow fiber nanofiltration, but also I may mix in direct nanofiltration. Direct nanofiltration is what we call it. The industry more calls it hollow fiber nanofiltration. I kind of use those interchangeably. More on direct nanofiltration, we call it that because most nanofiltration will require some pre-treatment steps, and we do not. You can handle the feed, generally speaking, directly. This slide right here will show you what our modules and membranes kind of look like. I'm not going to spend too much time on it, but you're going to see that they look very, very similar to UF or MF hollow fiber membranes and modules. You can see on the left, that's the module in a system. The cross section then of a module with thousands of membranes, thousands of the hollow fibers, again, very similar to a UF. Then you're going to see a cross section of a fiber itself. You're going to see the PES substructure and the nano layers that are of opposite charge, very robust nano layers. That is the core of our technology. Also, very quickly, I'm going to go through this slide here, which shows on the left what you typically think of when you think of nanofiltration. You think of what looks like an RO element, but it's a little bit more open. Has the spacers, has a flat sheet that's spiral wound, looks like the system on the top left, although that's a pretty small system. On the right is our module, and a diagram of our module. This is what we actually call our IRD module, which is an integrated rack design module. You can see it includes a header piece on the top and bottom, the element, which is labeled number 1 there, and Vitalics to connect the headers on the top and bottom. And then to the left of that, you'll see a plant that is actually operating to this day. When I talk about membranes, I should probably take a step back and say that the range of membranes that are out there are MF, UF, NF, and RO. That's from kind of more loose to more tight. MF is going to be like a 0.1 micron. UF will be 0.01 micron or so. Getting into Dalton range, it would be like 100,000 or 150,000 Dalton. Then getting into nano, it's tighter. For example, our nanofiltration membranes are 400 Dalton and 800 Dalton. There's another hollow fiber NF out there that's 1,000 Dalton. And then, of course, RO gets tighter, takes out more dissolved constituents. Just a little bit about our company. I don't want to drag this out too long, but our company and really the technology was born out of the University of Twente, out of academia, our scientists working on that. And then a company was founded based around this idea. Our first installation was in 2019 in the Philippines. And the other thing that I want to point out here was a very important date, which is in June of 2021. We had our initial public opening, our IPO of our stock in the Netherlands. And this was an infusion of investment money. And we use that for three things. One, to increase the production capacity of our plant. you see on the right, there's going to be approximately 120,000 or even greater than 120,000 modules that we will be able to produce starting, I believe, in 2024. So that's number one. Number two, it's personnel throughout the world, including myself. So like I said, the IPO was in June 2021. I joined in November 2021. And then the third thing is part of our strategy for piloting in new applications, new regions, different geographies. We require a lot of pilot units, different types of pilot units, and I have some photos of them at the end, but full-scale pilot units as well as benchtop pilot units to prove our technology. So all this investment money is used to really execute our strategy and get our product out there, because we really do feel like it is the next big thing in the water market. So the membrane itself is really designed around, and again, I mentioned before, it's 400 Dalton, there's an 800 Dalton NanoFiltration version. It's centered around organic rejection. What that means in the municipal side and in surface water treatment, municipal drinking water, let's say, TOC reduction. So we get greater than 70% TOC rejection with the membrane. Color removal. You can see that photo on the right where you have this tea-colored feed and you get a concentrate that's more coffee-colored and the product is perfectly clear. It's a really good representation of what we can do with this membrane. The other thing that we could do on surface waters is reject DBP precursors, and in this case, HA5. So on the left, you'll see it's a pretty clean water. It's only 0.4 NTU turbidity, but they have 2.2 or 2.1 TOC and DOC, but really they had an HA5 problem that was beyond the MCL, and they needed to take care of that. And the way they did that is with our membrane, the DNF. This is actually a DNF 80 membrane that did that. So that's the looser membrane, and it got the reduction of about 97.5 on the HA5. Now that's taking out the precursors, spiking it with chlorine, and then getting your HA5 reading off of that. This is a bit of a teaser slide, which I think is kind of interesting. So in Melbourne, Florida last year, we pilot tested. Currently, well, I should say it's a teaser because we're going to be presenting this, or rather Jacobs Engineering is going to be presenting this at the Membrane Technology Conference in February in Knoxville, Tennessee. We're very excited about that. They're going to go over the technical aspects of this pilot, but also the economic evaluation, which is extremely interesting. The current process that they have here, this is taking surface water in Florida. You imagine it's warm, it's very variable. You can see on the top left there that turbidity ranges from 0.5, which is real clean, to 97.7, color from 64 to 537 color units. Kind of crazy. It's a very shallow lake and things get kicked up from wind and all that. It's pretty interesting. So anyway, the current process: coagulation, sedimentation, ozonation, media filtration. It's an older plant. So what are they going to do in the future? They're going to replace it with a membrane system or membranes. And the two things that Jacobs piloted side by side here is an MF or UF module followed by your kind of typical spiral wound NF. And we said, hey, you could do that in one step. And that's kind of the key of our technology, is we can handle tougher feed waters than spiral wound nanofiltration can handle. So we say, hey, we can do it in one step. Now, remember, this can get kicked up to about 100 NTU. The TOC is also fairly high. So it's a pretty tough water to treat, especially directly. But we did that. And on the right, you can see the rejections. The turbidity, I mean, it's pretty much 0.03 or whatever, a UF will do. It's pretty much the same. But color and TOC to the right there is what's really interesting. And you'll see it at different recoveries. But really what we were gearing towards was an 85% recovery. And you're seeing the color is rejected something like 98%. The TOC in this case is rejected 95%. I said before that we do generally greater than 70%. And in this case, it depends on what is making up those organics, we did above 95%. So what we proved with the pilot, and again, there's a lot more to come out of that paper, but we proved this stable operation on this extremely variable feed water in Florida. And we also did it in one step, whereas, the alternate would be either the conventional approach would have multiple steps, or the alternate membrane would be an UF followed by NF. And that's generally speaking where our value proposition is. Our value proposition is reducing process steps. And what you'll see in this paper in the conclusion is that it's very favorable economically for us, generally on the CapEx side, but really on the total cost of ownership side. PFAS is another thing on our industry, which, we get questions, probably Alex and I, on a daily, if not, more often basis. How do you reject PFAS? What technology would you use? Well, we want to introduce ourselves as a technology for that and a membrane for that. I'm not going to speak too much about this, but I want to show just the membrane rejection of the different PFAS molecules out there. The DNF40, so it's our tighter membrane, the 400 Dalton membrane is the blue bars right there, and it's going to get on all of these greater than 90, greater than 95% rejection. The DNF80, which is a little bit looser, is really greater than 70%. Now, I should say that PFAS molecules, for the most part, are right around that cutoff, right around that, or rather, right around that molecular weight that is our 400 Dalton cutoff for the DNF40. But some are even tighter than that. But the way that our membranes are designed and the way that the membranes operate enable us to remove a great percentage of these molecules. Another slide, which will show something similar, is micro-pollutants. Specifically, what we're showing here, and this is kind of interesting when I'm sure everybody has seen that there are some residual of pharmaceuticals in effluent. So effluent that's taken from, you take your municipal effluent, you discharge it into a river, all of a sudden there's all sorts of different medications in the river. You can see here we have a whole host of them shown here, and the rejection by our tighter membrane, the DNF40. Cortisone, gabapentin, I know that one because my dog takes it. You may have heard him before barking. Ibuprofen, obviously everybody knows that. I don't even know how to say that one. That's a beta blocker, I believe. Propranolol. But anyway, it rejects these things extremely well. And that's another thing that we bring into the mix of what we can do and what we can bring to the water industry. So I mentioned surface water before, but now I want to mention secondary effluent. I only kind of want to mention this as we can do a kind of a potable reuse, whether direct or indirect. We could do that, but there are a lot of regulations in place. And so how do we actually fit into that? We don't yet know. We're working on that, but we know that there is something there. And this slide gives a quick overview of where we fit in here. What I think is really, really interesting here is that our membrane can operate like a UF in that you can take secondary effluent, which is pretty tough to treat because of the organics, and you could run it directly, like I mentioned, right into our DNF membrane or right into hollow fiber NF membranes, and they will operate kind of similarly. Okay, might be a lower flux. In this case, it's 15 GFD, but kind of similarly to how it would work on a surface water. In this case, we're getting pretty good recovery, 80%. And in this case, what we're doing is we're running it through the DNF and then into, I believe it's ultrafiltration, and we're proving we can create a drinking water out of that. Now, again, I don't know how we fit in with the regulations. In California, you need all these log removal virus in order to be deemed appropriate for drinking water, and understandably so. But we're proving here that it can be done with minimal steps and with our membrane. Just going to get into here, and this is kind of the last thing that I'm going to touch upon. I have a few slides here industrially. We have a lot of different applications where we employ our membranes industrially. And the light blue topics here are the ones where we are using the hollow fiber nanofiltration. So we're using it as a polish. We're taking a well water, we're taking a drinking water, or we're taking treated wastewater, secondary effluent, like I mentioned, and you're going to use the membranes to create process water. You're going to use it to replace this GAC, ion exchange, or UF plus RO to make process water. But you can also use it for brine recovery. You can treat the brine to increase the overall recovery of that system. Of course, we've used it, and if you move towards the top center, we've used it for boiler and cooling tower blowdown, internal process water in different industry. The DNF can be applied for chemical recovery as well. We have one off the top of my head. I know we're doing a caustic recovery. And then on the back end of the plant, either for reuse or for effluent polishing, you can use the hollow fiber nanofiltration membranes. The next slide here shows, and I'm not going to go through these, but it shows a bunch of different industrial applications that we've done, whether we've pilot tested, whether they're full-scale installations. We've done stuff like that. I just want to get down to the value proposition here. Industrially speaking, and it goes to the general value proposition as well, but industrially speaking, we're going to try to reduce process steps. I mean, that's the whole goal with hollow fiber nanofiltration is you don't need the pre-treatment to take out the TSS. It's going to do the TSS in one step as it's also taking out the dissolved solids. So you're going to reduce the process steps, whether it's a one-step process or it's a reduction of process steps. Also, because you're reducing process steps and reducing operations, you're going to ease operation, ease maintenance. It's one system instead of several systems. And really, it's the lowest cost to meet the goals. What we strive to do is by that reduction of process steps is to reduce capital cost and reduce OPEX. That's another thing, reducing power costs, reducing chemical costs. You're taking, again, multiple systems and making it into one direct nanofiltration system, which will reduce all of those things. This is kind of an interesting application, and I included it because I think I saw Alex post something on LinkedIn about Lake Mead. Well, that's a picture of Lake Mead right there. This is actually taking water from that area. It is not taking Lake Mead water, but what it's doing is because Lake Mead is reducing in volume, the areas around Lake Mead are really trying to recover, reclaim, reuse water that's used in process, water that's discharged, and use it for, in this case, for wash water. So I don't want to get into it too much, but what we're really doing here is we're getting the BOD down. You can see that the feed, and it's a contaminated well. It's got hexavalent chromium in there. It's got some nasty stuff, but really it's got BOD, and it's got TDS of 4900 and TSS of 50, and we're reducing it with the DNF. What we're doing is, and actually we tested it with the MBBR going into a DAF, going into a sand filter, and then they wanted to make wash water out of that. Well, it really didn't get to the quality level they need. So what we did is we got rid of the DAF, which unfortunately, Alex, that's what they did. I know you guys make a great DAF, but in this case, it worked really well, the DNF, right from the MBBR. So we rejected the BOD. We reject BOD something like 90, 95%. The TSS is going to go down to basically zero. TDS is only going to be reduced about 10% or so. But again, they use this water for wash water in their industry, in their factory right there. And you could see, you know, the kind of the typical feed permeate and concentrate streams. And it looks not as bad as the other one, but still pretty nasty, if you ask me. That's basically it. My last slide here, or maybe one more slide after this, but again, I'm stressing the one-step process. And I will say we are very excited because we have such a innovative hollow fiber nanofiltration membrane that's really based around and was developed around organic rejection. So the PFAS stuff, the TOC, the endocrine disruptors, all of that is rejected by this membrane. And what it comes down to, and the value proposition to the end user, is the lowest total cost of ownership. And that's my little teaser for the paper that will be presented at the membrane conference. I think it's February 20th in Knoxville, Tennessee. So if you have an application, please feel free to reach out to me. The next steps, generally speaking, when we get some water quality for an application, is we run a projection. You can see what the permeate will look like. We do some lab scale testing with the little unit that you see on the top there, and then get into maybe a full scale pilot unit so we can run different cleaning protocols, different recoveries, see what we can do with it, and then get into full scale design. So with that, I believe we'll go to Alex. Thank you so much.
Excellent. Thank you, Jay. Now we're going to open it up to some questions. I know that I have some of my own now that we're working without an audience. I guess I'm the one that's coming up with most of the questions. So here it goes. I did like how you're cutting out other processes. So you can, instead of doing a 6-process system, you could potentially go down to 4 or 3, which really helps when designing it and making sure that you pull off a mass balance. I did have a couple questions on pressure, or actually before I get into the pressure, energy. Of course, we're replacing these, or ideally we're using this kind of process replacing other processes. But as far as energy goes, how does this perform against a traditional nanofiber membrane?
So it will be similar 1-to-1. So if you were running a spiral wound NF, you would go to a similar pressure to reject at the same level. Where we provide savings is that we don't need the extra step of, let's say, a UF or MF, which is going to go, 1 bar, 14 psi, but even up to 30 psi upstream. So there's going to be, again, by the combination of those processes, there's going to be reduction of overall pressure. And when you do, typically speaking, a UF and then an NF or an RO downstream, you are breaking that head. You're putting, 1-2 bar into it. You're going into many times some sort of brake tank and you're repressurizing. So there is a savings there in energy.
Okay. I guess that kind of answers my energy question. I'm guessing that some of the energy savings that you'd have is that you're now reducing the amount of processes, right? So even if you were using 20% more energy for whatever reason, whether it's a pressure or chemicals, you are still replacing potentially a couple of the processes. So that would make a big difference. Okay. And then my other question was on the chemical enhanced backwashes. Like you understand how CIP works, but as far as chemically enhanced backwashes, are they any different than a traditional NF system?
Yeah, and I breezed through this presentation, so I probably skipped through quite a few steps here. And I do like to position our product against a UF. It looks like a UF, it operates kind of like a UF, but there are differences. So ours is inside out. A lot of the UF here in North America is outside in. Theirs is PVDF, ours is PES. The big thing, though, in terms of operation and cleaning protocol, we have crossflow. Generally speaking, a PVDF outside in will run in dead end mode. We have crossflow. That's one of the ways that we keep our membrane clean. The other ways are quite similar to what UF does, although we may do it a little bit differently. And I'll say, instead of doing a backwash, generally speaking, we'll do a forward flush. Instead of doing a CIP or a CEB, a chemically enhanced backwash, we'll do a chemically enhanced forward flush. And that doesn't mean that we wouldn't do a backwash and we don't do a CEB, but most often we do forward flushes instead of backwash. It just turns out over the experience that we've had, we found those to be the most effective.
Since you mentioned the forward flush versus a backwash, is it a shorter backwash cycle, or I should say, is it a shorter regeneration cycle, or is it about the same?
They're quite similar. They're quite similar. Yeah, okay. Yeah, they're quite similar. And similar cleaning chemicals, the cleaning chemicals that we talk about all the time, sodium hydroxide, sodium hypochlorite, citric acid, very, very similarly done. Yeah.
Okay. Well, you pretty much answered my last question as to what chemicals we're using if we're using the same kind of chemicals that we're doing, right? So that's perfect. No, that's great. So with that, thank you. Thanks again, Jay, for doing this.
Sure.
If anybody has any questions, his contact information is on there. Please also follow us on LinkedIn. We're pretty active on there. There's always a lot of new ideas as far as technologies, water qualities that we're willing to take a look at. There's some of the upcoming webinars that we have on electrocoagulation, ceramic membranes, and water risk management. And if you want to have a look at any of our past webinars, have a look at our channel. There's more coming out. I know that these were slightly older, but we've got some of the ones that are going to be coming out every couple of weeks. So with that, thank you very much, everyone, and I will see you next week. Bye.